There's something almost poetic about watching raw steel come to life. It doesn't matter how many times you've seen it, the glow of molten metal, the power of the press, the precision of a modern rolling mill, it never gets old. Today we're stepping inside one of the most impressive steel production facilities in operation, the Intermetal Manufacturing Plant. Pull up a chair, because this one's a real treat. Intermetal is a steel production company known for its vertically integrated process, meaning they handle everything from raw material intake all the way to finished steel products under one roof. That kind of control over quality isn't something every manufacturer can claim, and it's exactly why companies around the world trust them. The process begins with scrap metal, collected, sorted, and fed into electric arc furnaces, or EAFs. These aren't your grandfather's blast furnaces. A modern EAF can reach temperatures above 3,000 degrees Fahrenheit using massive graphite electrodes that conduct electricity powerful enough to melt solid steel in under 90 minutes. The heat is so intense it's visible from outside the building. Once the steel reaches the right temperature and chemical composition, and that chemistry is closely monitored by computer systems in real time, it's tapped into a ladle and transferred to the continuous casting line. Continuous casting is where things really start to take shape, literally. The liquid steel is poured into water-cooled molds and emerges as a solid strand, called a billet or bloom, depending on the cross-section, that moves on rollers and is cut to length. The strand caster at Intermetal operates continuously, day and night, with minimal downtime. From there, those billets head to the rolling mill. Heated to around 200 degrees Fahrenheit, they're squeezed between a series of powerful roller stands, each one applying tons of pressure to gradually reduce the thickness and shape the steel into rods, bars, angles, or beams. The rolling process also refines the grain structure of the steel, making it tougher and more uniform. It's not just shaping, it's improving the very nature of the metal. Finally, the finished products go through cooling, straightening, cutting, and quality inspection, including ultrasonic testing and surface checks before being bundled and shipped. At Intermetal, that whole journey from scrap to finished steel bar can happen in just a few hours. That's modern steelmaking. Fast, precise, and built to last. If you want to talk about American craftsmanship with real historical weight, look no further than the Watervliet Arsenal in upstate New York. Established in 1813, it's the oldest active arsenal in the United States. And to this day, it's the only place in America where large caliber cannon barrels are manufactured. That's over 200 years of forging history, and the tradition continues stronger than ever. Making a cannon barrel, or gun tube as they call it in the military, is no simple task. It starts with a massive forged steel blank, carefully selected for its metallurgical properties. The blank is then sent to one of the arsenal's most impressive machines, the radial forge, also known as a rotary swaging machine. This is where the real magic happens. A radial forge works by striking the steel blank simultaneously from multiple sides, typically 4 dies positioned at 90-degree angles around the workpiece, while the blank rotates and advances through the machine. Each rapid blow compresses the steel inward, not just shaping it, but fundamentally improving its internal structure. This process is called rotary forging or rotary swagging, and it's critical for cannon barrel manufacturing. The repeated compression aligns the grain structure of the steel along the barrel's axis, dramatically increasing tensile strength, fatigue resistance, and overall durability, sometimes by 2 to 3 times compared to simply machined steel. The result is a barrel that can withstand the explosive pressures of live fire over thousands of rounds without failure. After forging, the barrel undergoes deep hole drilling to create the bore, followed by rifling. The spiral grooves cut inside the barrel that spin the projectile for accuracy. Heat treatment, final machining, and rigorous inspection complete the process. Every barrel that leaves Watervliet Arsenal meets the highest standards of the U.S. Army. When precision and strength are a matter of national security, there's no room for compromise. There's a certain satisfaction in taking something that's worn down, beaten up, and just about ready for the junkyard, and bringing it back to life better than it was before. That's exactly what we're watching today, the full restoration and industrial chrome plating of a Clark TCVC-20M crankshaft. The Clark TCVC-20M is a large industrial compressor platform, the kind used in gas processing plants, refineries, and pipelines. The crankshaft at its core is a massive, precision-machined component. It can weigh anywhere from several hundred to over 1,000 pounds, depending on the configuration. The restoration process starts with a thorough inspection, dimensional measurements using precision gauges and micrometers, magnetic particle inspection to check for surface or subsurface cracks, and careful documentation of every worn area. Once the scope of work is defined, the crankshaft is cleaned and prepped for plating. Industrial hard chrome plating, also called functional chrome or engineering chrome, is the go-to solution for restoring worn metal surfaces. Unlike decorative chrome, which is applied in thin, shiny layers for appearance, hard chrome is deposited in much thicker layers, sometimes up to 0.050 inches or more, specifically to restore dimensions and add surface hardness. The process involves submerging the crankshaft in a chrome plating bath, a solution of chromic acid and sulfuric acid, maintained at a precise temperature. Electrical current is passed through the solution, causing chromium ions to deposit onto the steel surface at a controlled rate. It's electrochemistry at industrial scale. After plating, the journals are ground and polished back to their original or sometimes tighter tolerances using a precision cylindrical grinding machine. The finished surface must meet surface finish specifications, measured in microinches, typically in the range of 8 to 16 Ra. That's a mirror-smooth finish that allows the bearing to float on a thin oil film at high RPM without metal-to-metal contact. Of all the engineering achievements in modern history, few things are as jaw-dropping as a jet engine. And when it comes to the pinnacle of aviation propulsion, the Rolls-Royce Trent XWB stands in a class of its own. Developed specifically for the Airbus A350 XWB wide-body aircraft, the Trent XWB holds the record as the world's most efficient, large aero engine. And watching it come together on the assembly floor in Derby, England, is nothing short of breathtaking. The Trent XWB produces between 75,000 and 97,000 pounds of thrust, depending on the variant. To put that in perspective, that's enough force to lift roughly 40 fully loaded semi-trucks off the ground, from a single engine. And it achieves this with remarkable fuel efficiency, thanks to a very high bypass ratio and a sophisticated three-shaft architecture that's been a Rolls-Royce hallmark for decades. Assembly begins with the core engine, the high-pressure compressor, combustion chamber, and high-pressure turbine. These are the hottest, highest stress components in the entire machine. The HP turbine blades, for example, operate at temperatures exceeding 700 degrees Celsius, hotter than the melting point of the nickel alloy they're made from. They survive only because of intricate internal cooling channels that circulate cool air through the blade and a ceramic thermal barrier coating on the surface. Each blade is a small engineering miracle on its own. The assembly process is extraordinarily precise. Technicians work in climate-controlled bays, and every component is tracked with serial numbers and build records. Clearances between rotating and stationary parts are measured in thousandths of an inch. The fan blades, each one made from hollow titanium and composite materials, are individually weighed and balanced before being fitted to the fan disc. Even tiny imbalances at the 17,000 plus RPM the fan operates at can cause catastrophic vibration over time. Once the engine is assembled, it goes through a comprehensive testing regime. First on an indoor test bed, where it's run through a full performance profile, from idle to maximum thrust, while sensors monitor hundreds of parameters in real time. Any deviation from spec means the engine comes back off the test bed for investigation. Only after it passes every test does it earn its certification plate and get prepared for delivery. The Trent XWB isn't just an engine, it's a symbol of what human ingenuity can achieve when precision, materials, science, and manufacturing excellence all come together. Every time an A350 climbs smoothly into the sky, there's a Rolls-Royce Trent XWB making it possible. There's something deeply satisfying about watching a flat sheet of metal slowly transform into a smooth, seamless dome under the steady force of a hydraulic press. No cutting, no welding, no seams, just pure controlled pressure, reshaping the metal into an entirely new form. This process is called deep drawing, and it's one of the most elegant and efficient forming methods in modern manufacturing. Deep drawing is used everywhere: pressure vessels, aerospace components, cookware, automotive panels, medical devices. Anywhere you need a strong, seamless curved or hollow shape from sheet metal. And it all comes down to physics, making metal flow rather than fracture. The setup consists of three main components: the punch, the die, and the blank holder. The sheet metal blank, typically steel, aluminum, or stainless steel, is positioned over a circular die opening and held in place by a blank holder that applies controlled downward pressure around the perimeter. This blank holder force is critical. Too little and the metal will wrinkle as it flows inward. Too much and it won't draw freely and will tear instead. The punch, a machined tool, shaped to the desired interior profile of the finished part, is driven downward by the hydraulic press with tremendous, precisely controlled force. As the punch descends, it draws the metal blank down through the die opening, stretching and thinning it slightly while forming the dome or cup shape. For dome shapes specifically, the metal undergoes both radial tension and circumferential compression as it's drawn, a complex stress state that demands careful control of material thickness, lubrication, punch radius, die radius, and drawing speed. After the draw, the part may go through additional forming, trimming, or heat treatment steps. But that single hydraulic press stroke, turning a flat blank into a perfect dome, is where the real transformation happens.